name is Mark Sever. I'm a global application expert, food retail in Danfoss. I started in 1998 my journey in Danfoss and managing different positions. And what is important for today's session, I'm for a long time focusing on food retail applications. I have a lot of practical experience with HFC systems and since 2010 year I'm working a lot with CO2 systems, and I'm trying to spread this knowledge about CO2 systems and technology and news what we are developing to other countries, other continents, if we can say in such way. I'm a mechanical engineer. I would like to say for myself, mechanical engineer in the world of electronics. So combining these two technologies in one, it's a perfect match, I can say, for the dealing refrigeration systems. Okay. So today we will go through ejector systems. Particularly, we will talk about HP or high pressure lift gas ejector and liquid ejector technology as a kind of two separate technologies. But we would also like to show you an example where we combine these technologies on one medium-sized supermarket. We will also talk about system configuration, how it's designed, and what is probably most interesting are these measurements and what we did yearly analysis based on half-year measurements. At the end, of course, we will do a summary and we will have this question and answer part. Ejector product range, just to get familiar with the expressions what we will use. So if you look on the top, we have these high pressure lift ejectors with the acronym HP. And in the name of these valves or slash ejectors, there are numbers, and these numbers are actually mass flow in kilograms per hour at certain conditions. You see on the bottom these conditions, and these numbers are actually in the name of this valve. So in that way you can very easily understand for which system size these valves are designed for. Then we have in our portfolio also low pressure lift ejectors. It's also gas ejector, and it is for another kind of system. We will not mention them later on in this presentation. Then at the bottom we have a different kind of liquid ejectors, different sizes, which are specifically designed to do pumping liquid. And what I marked here as a red is this combi or combination of HP and liquid ejector. And actually this is today a presentation focusing on this solution. What does it mean? If you look this big block where we put different ejectors inside different capacities, this one consists of 5 vapor HP ejectors, different capacities, and then at the let's say most to the right in this picture is the liquid ejector, and all of them we are using to control the high pressure in the gas cooler. Anya, please, can you show colleagues how these blocks looks, let's say, in reality, how big is them, and so can you?
Yes, I can. So here you can see this is our the baby of all of our ejectors. This is the smallest one, what we call the CCMT1, because there can only be one ejector in here, as you can see. And here is a cut-through model that we use for exhibitions like this. So here you can actually see the core of the ejector. You see here where the flow comes in through the strainer first, because there's always a strainer in each of our ejector blocks to make sure dirt and other things are kept away from our valves. And then you can see how it first enters into the top of the ejector here. Then it goes down into the diffuser chamber, and then it is being, oh, and now I have to do this in the other side up around. There's a check valve here that is being lifted up, and then at the end it's being pushed out here through the diffuser and then out into the receiver here with this pipe here. So this is the smallest one where you can get an idea of what actually goes on inside an ejector, but we have an animation that explains that much better. So please come to our booth and I can show you that animation. It's much better. But just to give you an idea of what is a block actually. So now you have to be ready for this because it's a little heavy. This is actually how an ejector blocks look like. It weighs 10 kilos, so it's a rather big baby. But this is how our ejector look like. Over to you, Mark.
Thank you, Anya. To explain this combi ejector, I decided to talk about these two different technologies. And then, okay, we can in mind combine these two technologies in one block. So first of all, high pressure lift ejector system, or HP in a short way. What is it? What is for? It is a solution for the medium to large commercial refrigeration system with parallel compressors. So this is very important to understand. This is an add-on or enhancement of the parallel compressor system. Parallel compressors are often called with different names. It could be also intermediate compressor. It can be auxiliary suction compressor. So all of these names are actually meaning these parallel compressors. In our documentation, we are always using expression IT, or intermediate compressor. So later on, you will see a lot of these let's say, short acronyms for this suction group. Well, when we look this system in the cold ambient condition, the system is actually working like a standard booster system. Why? Because in the winter time, we can lower pressure in the gas cooler, and after the high pressure expansion, we will have a not so high amount of gas in the receiver, and actually IT compressor will be too big for this mass flow, and in that period of time we are using a gas bypass valve to relieve this gas to the suction of empty compressor. In this operation mode, let's say system is having a very high COP, so there is no let's say major drawbacks. The pressure in the gas cooler is controlled by these ejectors, or we can say also expansion valve, because ejector is also expansion valve. And if there is not enough capacity, then we are opening a high pressure valve, which is mounted in a parallel. So there is a logic in the controller to utilize first ejectors, and then if we don't have enough capacity to match the mass flow coming from the gas cooler, then the high pressure valve is jumping in. If we look this system, but in the summertime, we have a much higher pressure in the gas cooler. In this example, we have 35 degrees temperature out of the gas cooler on the pipe. It's not air temperature, it's measured on the pipe. The ambient temperature will be around 33 or close to 34 degrees Celsius in that condition. The pressure in the gas cooler will be on the level of 90 bars. And if we manage pressure in the receiver, in this case 39 bars, we will have a quite high pressure difference, and this high pressure difference will enable us to pull or suck the gas from the suction size of the empty compressor. So the goal here is to take a part of the gas which should be taken by the empty compressor, and through the ejector it is delivered this gas to the receiver, and this additional gas will be pulled out by the IT or parallel compressor. On this example, you can notice that from the receiver, this gray number is 57%, meaning 57% of the total mass flow is liquid. But after the evaporation in empty and LT evaporators, so it's gas, the mass flow is split in this example 22% to the ejector, and only 35% of this original liquid which is entering to the subcritical area is only 35% is going to the empty compressor. So part of this flow we deliver to the IT compressor, which is, as you can see now, running on a very high capacity. So this is the goal of the system. What is very important is that we are controlling pressure in the receiver with this optimal receiver pressure, because by doing this, we are actually controlling what is the entrainment ratio. And entrainment ratio is ratio between how much we are sucking, how much gas we are taking, and how much is the mass flow entering to the ejector. So this pressure in the receiver is very important part of the algorithm, and it includes also pressure in the gas cooler and what is the pressure on the suction of empty compressor. So all these pressures are somehow aligned. You can see here with the dotted line in the log pH diagram that this gas, which is sucking, ejector sucking from the empty suction group, is delivered to the receiver. And the line is a bit tilted from this high pressure expansion. In reality, it works a little bit different, but the point in the receiver where you see this 53% of the gas fraction is actually a result of the ejector work. From the other side, when we look other technology, it is a liquid ejector system. It's a bit different idea, let's say. The idea here is to use a new developed algorithm, what we have in our evaporator controllers, to use a different superheat control. What does it mean different? We used for many years and still using, of course, a superheat algorithm, what we call minimum stable superheat. And when we are running this algorithm, we don't have any parts of liquid going out of evaporator. But shortly, we can say this is a dry expansion system. There is no liquid going out. But with this technology, we wish to go a bit more deeper in the evaporator and to utilize better surface for exchanging heat. So we are using a superheat control algorithm, what we call adaptive liquid control. By doing this, we are managing to lift more pressure on empty suction line because we are better utilizing evaporator surface. But as a drawback of this technology, we are getting few drops or certain percent of the mass flow liquid going out of empty evaporators. And because of that reason, we need to use a suction accumulator, and you can see on the diagram there is a suction accumulator where we are collecting this liquid, and the liquid ejector is used to pump this liquid to the receiver. I would like to emphasize here that beside liquid ejector, who has this possibility to lift the liquid in cold ambient condition, in warm ambient conditions, we are also using HP ejectors to lift the liquid. So we are using both these technologies to take liquid to the receiver. So warm condition, as you can see on this example, and this is example, let's say, without utilizing HP ejectors. you see the log pH diagram looks, let's say, exactly the same like in the standard system, but the pressures are different. The pressure on empty evaporator is higher than in previous examples. Actually, what we are doing savings on empty suction group because the pressure is higher. What is CALM? CALM is acronym for CO2 Adaptive Liquid Management, which consists of different technologies, let's say. First of all, on the pack controller, we are utilizing a PO optimization feature, which is governed through the system manager as looking which one is the most loaded evaporator on, in this example, empty suction line, empty evaporators. And then based on this worst case cabinet evaporator, the pressure is lifted up or down in the system, in the pack controller. The second important stuff, we are controlling temperature in those evaporators with modulated thermostat. Controllers has to be those which has a minimum stable superheat control algorithm and also adaptive liquid control. By utilizing these two technologies, only the most loaded evaporators will operate with zero superheat or the minimum superheat, of course, depending on the settings. What is happening if ejectors are not capable to lift all the liquid which is accumulated in the suction accumulator? The level will rise at a certain level, and in this example, the level switch is between this green and yellow area. This indication of the level will come to the pack controller. Pack controller will send this signal to the system manager. System manager or the network unit will send this information to the evaporator controllers. Stop adaptive liquid control or adaptive superheat control, liquid superheat control, and switch to the minimum stable superheat control, or in other words, in a dry expansion system. So not to, and then the system will stop releasing liquid to the suction accumulator. In that way, you are giving a system possibility to get back to the normal, or let's say standard operation. Of course, normal is also with the adaptive liquid control. The point is to get to the standard system. So this is CALM. Question is how much evaporators are, let's say, most loaded. This is very typical question I am receiving. And if we are talking about the supermarket application where we have multiple evaporators, similar sizes, we are talking about 2 to 5, 6 kilowatts. Then we can say that the ratio between evaporators which are most loaded and which one are releasing this liquid to the suction accumulator, and we can say on this kind of applications the average value is always below 30%. Here you can see example from the case what we will present today. It's a 2 weeks period where you can see that very rarely this ratio of most loaded evaporators are amount of evaporators are going above 30%. As you can see, in average, it is somewhere around 20%. But in general, we can say it's a 30% to be very sure. So this was a bit more introduction to the technology and to get better understanding what we did test on this particular system. System is it's the supermarket chain Edeka Fausten. It is in Germany, so it's positioned in let's say Central European climate zone. And well, it was startup of the system was done at the end of 2019. We managed to install energy meters during springtime, and you will see when we start recording from this system. System is medium size, as you can see, medium temperature capacity 70 kilowatts, low temperature capacity evaporators. We are talking about now refrigeration loads is 16 kilowatts. What is interesting to add on the gas cooler, we have a three-way modulating bypass valve. In that way, we can very close control temperature out of the gas cooler in the cold ambient condition. And also when we are maximizing heat recovery, we can completely bypass gas cooler. Heat pump evaporator, let's say, is integrated in the gas cooler, and well, this brings a beneficial operation when we are using heat recovery operation. What is also interesting that on this plant there is no additional heat recovery. There is no additional heat source. The only source for heating is coming from the refrigeration system, and it's on the level of 110 kilowatts. How the pack is configured. So we have three empty compressors. One of them is variable speed drive compressors. There is one IT compressor, and all these compressors are same size. I mean, same designation. Only you can notice here on each suction group there is one variable speed drive compressor, or it means we have a frequency drive mounted on it. Then we have, of course, LT compressors. Here we also have three compressors. One of these compressors is variable speed drive. And as you can see here, we have a high pressure expansion valve, a CCMT 16, and the combi ejector. I mentioned before what is the logic. We are utilizing, first of all, ejector as an expansion valve, and then when we don't have enough capacity to match multi-flow coming from the gas cooler, only then we are opening high pressure expansion valve. How it looks, this system in log pH diagram. So now we are talking about this combi ejector. The diagram looks, let's say, the same like for the HP ejector, but only difference is that empty suction pressure or temperature is higher than in the previous examples. So this is what we are looking for, and now let's see how it looks in reality. In reality, this is a installed pack. If you look on the photo on the left side, on the far left of the photo, you see a suction accumulator. It's here like a separate, let's say, separate. It's like accessory for the main pack unit. On the far behind, there is a suction accumulator, and on the photo on the right, you see the suction accumulator, and then behind that is the ejector block, what Anya also showed you a bit before. You see three LT compressors, and then on the bottom you can see four same kind of empty and IT compressors. And measurements. To emphasize once again, we did analysis for this conference utilizing conditions when we don't have heat recovery condition. Meaning, you see here two different schemes. All of them are from our manuals. The picture photo on the left is showing a system operation without heat recovery, and we are controlling pressure in the gas cooler following this black line in the subcritical and transcritical operation. On the right side is actually algorithm how we are controlling system when we have a heat recovery request. What we are doing, first of all, we are increasing pressure in the system, and after this first step, then we are also, let's say, increasing the temperature out of the gas cooler, and by doing this, we are managing to have a higher and higher heat recovery for the system. As I mentioned you on this plant, there is no additional heating source. So the system operation on the right is excluded from today's analysis. This is important to understand. The second, what we did in the system, so always when you are doing this technology comparison, always is a question, what is the reference? What is the store reference? Here we have exactly the same store. We are not changing anything else in the system. We are not changing any parameters, only we are switching on and off following technologies, let's say. On the left side, you have operation working like a standard IT operation or standard parallel system. I disabled Calm, let's say, with what is set it up in the system, or this adaptive liquid superheat control. And I also disabled HP ejectors. So the whole block I disabled. And then the system is working only with the high pressure expansion valve. You see on the top left corner, green, let's say, sign for the high pressure expansion valve. On the right side, you see when ALC operation is turned on, or the calm is turned on, and also the HP ejectors is turned on. And you can see next to the high pressure expansion valve, yellow sign, it's also on. But what we also noticed that in this system, when the combi ejector is in operation, it is sufficient to manage all the mass flow coming from the gas cooler. So in practice, this high pressure valve is here just, let's say, waiting just in case to be open. Weather measurements. We started measurements as beginning of July last year, and we have measurements from the nearby meteorological facility, and also we have a ambient temperature measurement which is entering to the gas cooler. And you see that these two temperatures are aligned. There are minor difference between those two measurements, and this is presented in this gray line, which shows that the difference is between 1 to 2.5 degrees Celsius approximately. The little bit bolded lines are average trend lines for every day, so in that way you can easier see what is happening in the system. We change different operation modes. As you can see, in the summertime, we run system only utilizing HP ejectors. So I switched off Calm. Calm was switched off, and then later on in the let's say beginning of September, we start the system to work as a standard IT system, and then at the end of October, we started, let's say, full system with HP and the Calm or LC operation. Just for your information, beginning of March, we again switched off ejectors to see how the system is operating now in this, again, a bit warmer condition. And then, okay, we are planning to do more tests to have, let's say, one whole. Operation measurements. What are results for the moment? So this is a result of operation of combi ejector, where we can see this is the evaporation temperature slash pressure. You see on the right side on the diagram this small yellow dot. It's the position where we are measuring this. So you can see that at different ambient conditions, we are achieving this higher pressure ahead of empty compressor. In average 2 to 2.5 kelvins we can manage. We also can notice that when the ambient temperature is higher, the slope of the line is going lower. And this is, of course, logical because at higher ambient conditions, we also have a higher temperature in the supermarket area, meaning also we have a higher humidity, and there is, of course, higher load on the cabinets. So in that way, of course, the suction pressure optimization is, let's say, decreasing pressure to match desired capacity. But as you can see here, we are managing this advantage. Second effect, what we can notice is decrease of the suction superheat on empty compressor. You see black line is a standard system and green line is with utilizing a combi ejector. Here we have why these two lines are going to be aligned at the higher ambient temperatures. There are two effects. One effect is that HP ejector is capable to pull more this gas from the empty suction line, meaning this cold gas coming from the empty evaporators will be less and less. This is one effect, and second effect is that LT discharge temperature will be higher. You will see on a following slides this effect, because all this is connected in this area where we have this blue line. All this pressure temperature are connected somehow, thermodynamically, of course. So here you can see what is happening with the LT compressor's discharge temperature. We have increase of the temperature. So in average, coming from the 70, let's say 2 degrees, in average, it is lifted to 77 degrees in average, let's say, in all this period. Why is this so? Very logical. We increased suction pressure head of empty compressor, and of course, then the discharge line from the LT compressor is, of course, going more to the right in log pH diagram. So, of course, the temperature is a bit higher. So, when you understand the system, how it works, this is at the end logical. But this increase is, as you can see, not so drastic. What is happening with the medium temperature discharge medium temperature compressors discharge temperature? It's because of all these effects, higher evaporation temperature, lower superheat. The result is, of course, that the discharge temperature is also lower. This also brings benefits for the lifetime of compressor, because every degrees higher temperature, higher discharge temperature is, of course, having influence on the lifetime of any equipment. So it means also compressors. So this is also plus to the system. What is happening with the IT compressor discharge temperature? So with the higher ambient temperature conditions, we see that these temperatures are aligned. And this is what we expected, because we are sucking directly from the receiver. I mean, in the receiver, we have we are on the saturated line, but after the receiver there is also plate heat exchanger to do additional, let's say, superheating this gas, so not to be on a very low superheat on the suction of empty IT compressor. So it is expected that these two lines are aligned. But what we see at the lower ambient conditions here, some, let's say, not aligned situation, and we believe this is just a matter of statistical error, because we have, as you can see here, few dots of these green dots, which are with the higher temperature, and because of that, the trending line is going, let's say, too high. The explanation can be where these dots are coming. I mean, why we have some situation with the higher temperatures here. Don't forget that we are running this system also with the heat recovery, and this could be residual measurements or high temperature after the heat recovery process. So I didn't mention before, but let's mention here. This dot here on all these graphs represent in every 15-minute cycle average value. So we also looked in every 15 cycles, is it in heat recovery mode, is it in normal refrigeration mode, and every measurement what we are presenting here is average value in that particular 15-minute cycle. So this is what we have for the moment, but with the more measurements, we are expecting that these two lines will be aligned. What is, let's say, one of the most interesting slides or diagrams to present today to fully understand the influence of these ejectors technologies. In the controller logic, you have always information about how much your suction compressor group is loaded, how many in percentages. And on the left side, you can see this blue line showing empty compressors from 0 to 100%. Don't forget, we have here 3 compressors. And you see this red line for the IT suction capacity. It is starting somewhere around 21, 22 degrees Celsius, this trend line. And you can see how few dots we have when IT compressors were, let's say, engaged. But when we start with utilizing combi ejector technology, HP and liquid ejector, you see that the starting point of this trend line is somewhere around 16 to 70 degrees Celsius. And as you can see here, we have much more engaged IT compressor. As you can see, it goes also to the full load, to the 100% of IT compressor capacity. But also you can see that the empty compressor trend line on this higher temperature is going downwards. So it means we are actually really moving this gas, which is in a standard system, which should be taken by the empty compressor. Now we are moving all this gas, not all, but a lot of this gas to the receiver, and then through the receiver to IT compressors. So this is a very good example how the system is operating. So these are, let's say, thermodynamical or operational measurements. Concerning energy consumption, so we put the energy meters on each compressor, and on the left side you can see measurements with different technologies in kilowatt hours per 15-minute cycle. On the top curve, it is a gray curve. This is no ejector technology. Then a blue curve shows utilization of HP ejector. This, if you remember, this was the last summertime we used these measurements. And then for the HP and liquid ejector technology, we have, let's say, not so many measurement points. And what we have today, we have this gray line, which is a bit quite low. And we, let's say, to be very fair, we didn't utilize this line for the further calculation, because we believe more realistic is to expect results what we will have in the autumn time, covering this dotted green line. And we took these lines and utilized these models for predicting yearly consumption. What you can see on the right side, and you can see the numbers are now showing kilowatt hours, of course, in 1 hour operation. We took weather data for the Düsseldorf, and we counted number of hours in the year at certain temperatures, and you can see here what is the climate in that zone. And you can notice that there is not so many hours above 20 degrees Celsius. So it's in average below 100 hours in the year. But by utilizing HP ejector, we are entering a bit more to this 17, 16 degrees Celsius. So we have more hours we can utilize this ejector. It's very important to understand what is the climate in that zone. And we did a yearly analysis for every hour. So it means 8,760 plots, and we summarized per month, and here are results showing savings through the year without heat recovery. This is very important to say. So you can see in this, even in a mild climate, we have this savings. You see on the right side per month, the green tab or column is showing operation with the combi ejector, and the black line shows average monthly temperature. When we took this savings in kilowatt hours, we multiply with the average value for kilowatt hours this supermarket chain is paying, we get on a yearly level savings of roughly around 1,200 euros per year, again without heat recovery utilization. As a summary, we can say even in a mild Central Europe climate, we can see additional energy savings using these two technologies, vapor and liquid ejector. We can also say that this combi block or this combination is a perfect solution for the medium-sized system. What is very important to note, for the parallel compressors. So immediately when you have parallel compressors, you can think about this technology. Note, I mentioned this a couple of times, this is analysis or results without heat recovery. We are expecting also to have very nice results utilizing these technologies, but of course we have to have a whole winter time operation at different operation modes. And those field study results will be shared later on danfoss.com. So now we are to the question and answers. Anja?
Maria, and you have been quite clear, so there's not so many questions, but we have a few. So the first question, Mark, is what kind of sensor is used for the ALC or adaptive liquid control to measure the liquid level?
We are not measuring liquid level after the evaporators. We are measuring superheat. So we are using the same temperature sensor and same pressure sensor, what we are using for decades technology, and only we are measuring superheat. The liquid level in the suction accumulator can be level switch from any brand which is specified for CO2. this level switch, which will turn off, which will be used in the calm solution to turn off ALC superheat control in the evaporator controller. Okay, next.
Next question then, Mark, and that is about heat exchanger. One of our guests here can see that we use an internal heat exchanger in the ejector cycle. What is the influence of the internal heat exchanger on the ejector?
It is just a sec. Oops, yeah, just I suppose we are talking about internal heat exchanger after the gas cooler. So this heat exchanger is important when you use parallel compressors. Why? Because if you don't have this exchanger, you will suck gas at a saturated line from the receiver, and every pressure drop you can have in the line, also filter if you have in suction line, and in the compressor, all this can of course create pressure drop, and you will enter to the mixed area, and you don't wish to be in the mixed area in front of the compressor. So because mixed area means liquid, so this is important to use this plate heat exchanger. If we are talking about influence on the ejector as it is, it means that you will have like a small additional subcooling from the gas cooler, because you will do subcooling of this liquid going from the gas cooler, and of course it will have an influence on ejector operation. Yeah, it will have a small influence, but not so big one.
Thank you. We have two more questions to go, Mark, at this point. Next question. How much could be saved if going to a warmer climate like Portugal?
Good question. Of course, in Portugal, the climate is a bit different because just to show, for example, this slide, there will be absolutely more hours in the year with the temperatures above 20 degrees Celsius. So simply, this is important to understand the climate zone. I also noticed Portugal doesn't have so extreme, extreme temperatures. When I'm talking about like 40 degrees Celsius, like for example in Spain. I suppose it's more influenced from Atlantic Ocean, that the climate is a bit influenced by this huge water, of course. But absolutely, when we are looking at this weather profile, Portugal has a lot of hours above 20 or above 70 degrees Celsius, where you could see the huge influence of HP ejector technology. Yeah, but yeah.
More questions coming in, Mark. So next question here. How do you size a parallel compressor for these configurations?
Also very good question. There are different strategies how to size a parallel compressor. What is good to understand personally, so there are different philosophies from different OEMs, but my philosophy will be to utilize IT compressor more number of hours in the year. Meaning, there always is a challenge when you can start your IT compressor, when the minimum speed of your compressor is capable to control pressure in the receiver in a let's say stable way. If you start your parallel compressor too soon, meaning it has a too high capacity for the amount of gas in the receiver, then you will notice oscillation in the system because the pressure in the receiver will drop down, then you will get in the pump node load condition, then your gas bypass valve will start to operate, and then again you will switch to the IT compressor, so you will see really oscillations in the system. And this is all these oscillations are reflecting from the receiver to the suction of empty compressor and also on the discharge of the empty compressor. So the very important is to have a stable control in the receiver. Coming to answer, so if you select your IT compressor, just imagine you have one IT compressor. I would rather have a smaller size of compressor and then utilize more number of hours in the year, so I can start this compressor even when it's, let's say, 10 degrees or 12 degrees ambient condition, and then when this compressor is on full speed, then the rest of the gas, if it is created in the system, then it will be released by the gas bypass valve to the empty compressor. What I also found on many installations is that the pack as it is a bit oversized, and it means you have a lot of redundancy in the system. So it means when you have a big IT compressor here and you design it in a, let's say, extreme conditions in the summertime, this compressor will rarely will work. So for example, in this slide here, you notice that on the left side, the number of points and the number of hours in the year is quite limited. So it's, you know, we are talking about 100, 200 hours in the year will work. So rather have a smaller IT compressor and to have more hours in the year to operate and utilize this technology. Anya?
Good, Mark. Good. Then we have one more question. And so if anybody's sitting out there who have more questions, please make sure to type it in because we still have 7 minutes to go. But the last question that is in here right now is actually about something we're not talking about today. So you are free to say no, Mark, but I'll try anyway. And this is about the heat recovery for heating. If we rise the pressure of the gas cooler, meaning that the COP of the refrigeration gas cycle gets lower, is there a point where this becomes less efficient than using a different system for HVAC?
Good question too. For example, on this plant, there is no additional heat source. And so all technologies is in one, let's say. If you look at this system when it's running in a heat recovery operation, and of course you are losing efficiency if you just exclude the heat recovery utilization and you look in the refrigeration system. Of course the COP is going down because you are typically going to the 80 bars in the gas cooler, and in principle this is in normal operation summer condition. So but if you look at the whole system, you are always in plus. It's really good match to utilize heat recovery in the refrigeration system, particularly on CO2 system, because we are entering to this transcritical area where we can not utilize only the superheating area like in the HFC system, but we can utilize complete. If you go to the log pH diagram, just a sec. We can utilize a whole area on the high pressure side to have a heat recovery. So because of these transcritical possibilities, CO2 gives huge advantage with the heat recovery.